Okay,
Right.
great. All right, hello. So this is going to be about population effect estimation and hierarchical models. This was joint work with Nick at Stanford. Actually, Bob introduced me and him. And about a year ago, we had this idea. If you want, you can get the slides and the code here. I'll give you a moment if you want to grab that. There's a lot more, so there's about 40 slides, but we're only going to go through, I don't know, about 15 of them. So there's a bunch in the appendix, and you can see a lot more. All right, so I'm going to kind of build up what we did here, and we're going to go sort of slow, and then you're going to get a bit more as we go through, and then the implications of what was done. So what is just the sum to zero constraint? So now, this is something that we put into Stan maybe about a year ago, and since then, people have been using it. We've had some case studies. Mitzi wrote a really nice one, and it's really helped out a lot of these models because it identifies this one extra parameter that you have, and you can fit these things much faster. What I'm going to show here is something kind of neat in that you can actually get the Bayesian estimate back out by using the sum to zero. So you kind of get the best of both worlds. And I'll show that in a second. First, what is a sum to zero constraint? It is exactly what you think it is. You have this vector, and it sums to zero. So you might think that, hey, an easy way to do this is you take your parameters, your n minus 1, you sum them up, and you take the negative of that to get it to sum to zero. So you can see that here, which is yn, and you set it to that, and then you can see, okay, z is going to sum to zero. Now the problem with that is that you don't have exchangeability. You're not treating all of your parameters alike. And so what we have here is, this is if we had a uniform distribution on 4 of our parameters, and you can see that, hey, if we take the sum of a uniform, you're going to get this nice bell curve, but each uniform one, if you're doing it between -1 and 1, is going to be that blue curve. Now, these are going to be treated differently, and you're going to get high correlation on that summed value, and you don't want that, or typically you don't want that, because you're putting a very strong prior assumption into your model. All right, so what we do in Stan, and what I think they also do in PyMC, is that you do this, you have this orthonormal basis for the sum to zero constraint. And so what we're doing is we're taking it and we're treating sort of all the parameters equally, or so they're all getting the same sort of effect on this. So now they become isotropic, meaning they each have that same effect, and they become exchangeable. So what you're seeing here is you're taking those parameters and you're applying this orthonormal constraint, and then it just goes into this subspace, which is that plane, that now sums to zero. Okay, now we're going to switch gears a little bit, because now we have to talk about hierarchical models, and we're going to talk about 2 flavors. We're going to talk about Bayesian hierarchical models and sort of what happens there, and then in the frequentist world. And you'll see why I'm sort of contrasting these two. So the big thing here is that we can treat, in our Bayesian world, we can treat everything as a parameter. We have this global population distribution. We get this nice partial pooling effect. Everything is sort of jointly estimated. You're sharing information. Great. I think everyone's very familiar with that. So we're going to move to the next one. All right. In the frequentist world, there's just no population distribution, right? Our thetas here are fixed unknowns. They're not draws. And so what they have to do here is they have to do a constraint. This is sort of an effect coding constraint. One way of doing that is a sum to zero constraint. All right? And we often see that in frequentist hierarchical models, they're fit much faster than Bayesian hierarchical models. Now they're doing a lot less, right? All right. What we get here is we can see that for our hierarchical models, we have our population parameters, alpha and beta. So if you had a varying intercept or a varying slope, we're going to focus on the varying intercept thing, but the arguments that I'm going to go through here, they all apply to the varying slopes as well. And then we can see that, okay, we have this A sub j, and we have B sub j. And those are the things which we're interested in here. All right. Now, just to kind of make this point a bit more, in our Bayesian model, we have our alpha and betas, right? And we have, well, those should be A and B. And then we have alpha and beta, which are population parameters. And we're actually going to almost like draw from our assumed distribution. So we have AJ and BJ, and we're going to draw those from normal alpha sigma A, and similar for B. For the frequent disaffects coding one, we don't have that. We just have our population parameter there, and you can see that we have that sum to zero constraint, hence you get this identity there. All right, so if we just restrict to the varying intercept, and we look at this, how can we move between them? Is there a way to move between them? In the easiest way, let's start at the Bayes level, and let's just look down there, and we can see the sum to zero, so I'm going to use that subscript to denote what we're doing here. So in the Bayesian world, what we can do is we can sum up our varying parameters, and then we can just take an average of those. Okay, so that's alpha, or sorry, A with the bar. And so our sum to zero thing, hey, we just do that, and then we subtract the same thing. So we're just summing and subtracting, and it actually works out. You kind of have to believe me. So what we'll do, we'll just do some empirical evidence here. We'll do some simulation, and we're going to have this unbalanced group simulation. So you have alpha 5, sure, whatever. We have some parameters. We have some sizes, different sizes, 8, 13, all so on and so forth down there. And then you can see what, for this draw is, we have our A bar, 0.85, alpha sum to 0, 5.85. We'll do 10,000 iterations. You can see what I'm doing here. I got to put stan code, it's StanCon. All right, so we have in the generated quantities our recovery there. So you can see here, I actually have J parameters. This is like a standard. This is what you would see, everything from the parameters and model block you would basically see in the manual. So we have J parameters. This is not sum to zero or anything like that. And then we're recovering it in generated quantities. And what do we do? So if I fit the sum to zero one and I fit this, okay, they actually agree. So you can recover it perfectly, and it agrees in distribution. All right, so the other way, though, and this is the more interesting way, because this is the way that everyone should be using here. This is the way where you actually do the sum to zero, and then if you want to recover those Bayesian estimates, this is how you would do it. It's all based on basically conditional distributions and marginal distributions. I'm not going to go through all of the math here, all right? But what you'll see is that as you go through here, we have this A bar. It's conditional on the alpha sum to zero. So that's the population parameter from the sum to zero. And tau. And tau is the population standard deviation. And what you get from that conditional is you get that it follows this normal distribution. And we have W, alpha sum to zero, and BC. And then you'll see down below what those come out to be. And this is all properties from the normal distribution. All right, so for each of them, we can sample this realized mean and shift the coordinates. And there's quite a bit of stuff going on here. And you can see in generated quantities kind of what happens. Now, I think the most interesting thing here is if you look at line 20 in the code, you'll see we have normal underscore RNG. All right, so what are we doing here? So in the sum to zero, what we do is we have, we're parameterizing this with one fewer degrees of freedom. We can draw that back out, okay? And this is a prior draw. It's based on our prior distribution. And we can draw that back out, and we can put that uncertainty back into our estimates. And that's how we recover our Bayesian estimates from sum to zero. All right, so the two fits agree. in this sense too. But the thing that's most interesting here is that it is about 100 times more efficient to do sum to 0. So we have exactly the same way, right? We can recover in distribution how we're doing this, but we can do it 100 times faster in Stan today. Why aren't you doing it? All right. So the idea, right, it's very simple. We're just using the decomposition. We're going to do the sum to 0. We're going to have this induced prior, and we're going to use our properties of the normal distribution. And now I do want to say something. This actually extends to elliptically symmetric distributions. So it's not just normal distributions. So student t, Laplace, those distributions, they're game. You can use it for this. All right, I have maybe 7 minutes or so, okay? We're gonna do something. This is relatively recent, at least for Nick and I. We extended this idea to group-specific standard deviations. So you often have prior information about the uncertainty of your varying intercepts or your varying slopes, and you want to encode that into your prior. This becomes hard to sort of do in this method initially, and then we kind of figured out, actually, no, you can do it, and the argument extends pretty similarly to what we had just gone through. You just have to do everything on the log scale. So what we see here is we see this Sj, okay? So this is where we're going to do the stuff on the log scale. So we have this gamma in Bj, and this B is different than the previous B. This is not varying slopes. This is the standard deviation on our varying intercepts. All right, so we go through, and what you'll see here is a bunch of math. And this is just to convince you that I've done my due diligence, and that it works out. It's it's basically just the same argument that we went through, but now we have the standard deviation, and we have to kind of go through a little bit more, and we have this sign, and so you see this lambda that comes up there, and so we have this positive and this negative, but it induces the same normal distribution. All right, so then we have to go through the math, the properties of the normal distribution, and then we can recover all of this stuff. And now I want to show you how that works. And that, once again, it's the same slide over and over again. It's all the same. It becomes exactly the same as if we had fit this without. But the thing that's most interesting here is that it is much, much faster. All right, so 0.7 seconds it fits. Efficiency is huge, and ESS per grad is much more efficient. All right, and you see the same thing here. Interestingly, the standard deviations on the conventional one is actually fit, or like the ESS there is pretty good, but all the other parameters are fairly low. And then what I mean by the mean there is this is the mean of the varying intercept AJ and the varying standard deviations SJ. I just didn't want to put them all on the same slide, so I just took the mean of them. All right, so this slide here, this is going to show us a log plot of the leapfrog steps on the log scale. And so what I did is I extended the simulation out. And so I said, okay, what if we had 10 groups or 100 groups? How does this scale? And how does this scale versus the conventional model? And so you can see we still get, we get basically linear scaling in the sense of the ESS per grad. But for the conventional model, for the varying effects, it drops quite a bit. And who knows? I don't know. I didn't want to wait any longer. So if you just extended it out to 1,000, I don't know if that, I imagine that would keep dropping, but we'd have to see. All right, so this is not magic. So I always thought when I first thought of Bayesian hierarchical models that, hey, we could somehow estimate this superpopulation. And if you had a new group that you wanted to draw from, you could do it because you estimated the superpopulation and everything. And the frequentists, they couldn't do it because they didn't have this. But it's really just a property of the assumption of that distribution. And that property just means it's not magic. We're just drawing actually like a variate from this prior distribution and adding that uncertainty to our values. So it's kind of unfortunate in some sense. This is like a negative result, I think, in some sense. But it means, understanding this, it means that we can get this really efficient way of estimating these models, and we can do it today. And then, so Nick and I will have a paper, and we'll spell it out a bit more clearly, and we'll include like multiple sets of varying effects, the varying slopes, and then the extension to the elliptically symmetric distributions.
All right.
Thank you.
Let's thank Sean for a great talk. Okay, we have time for a question from the audience. We have Aki up in the top.
I talked to Paul about this earlier, so yeah. Hopefully, I don't know. We'll vibe code a pull request in the next hour.
All right, let's thank the speaker again.